Welcome to the HEOR Insights YouTube channel. This explainer will provide a foundational understanding of how to interpret forest plots, which is a critical skill for any professional in health economics and outcomes research, or HEOR.
Our session is structured into 5 key areas. We will begin with the definition of a forest plot, then break down its core components. After that, we'll walk through a systematic guide to reading a plot, learn how to interpret the pooled result, and finally, discuss its practical applications in HEOR.
So let's start with Section 1. What is a forest plot, and what is its role in evidence synthesis?
A forest plot, which is sometimes also called a blobogram, is the standard visual tool for presenting the results of a meta-analysis. It's designed to display effect estimates and confidence intervals from individual studies and then synthesize them into a single overall outcome.
In the field of HEOR, forest plots are absolutely essential for a few reasons. First, they synthesize evidence from multiple clinical trials, allowing us to see the consistency of results at a glance. Second, they are a mandatory part of health technology assessment, or HTA, submissions to bodies like NICE or CATH. They provide the justification for the clinical inputs used in economic models. And third, they help us assess the feasibility of conducting a network meta-analysis by checking for any major inconsistencies between studies.
Moving to Section 2. Here, we will deconstruct the plot into its 6 core components to really understand how it displays information.
At a high level, every forest plot contains these 6 elements. On the left, you have a list of the individual studies. The horizontal axis across the bottom shows the scale for the effect measure. Each study's result is shown as a box with lines, or whiskers. There's also a vertical line, called the line of no effect, which is our reference for significance. And finally, the diamond at the bottom represents the combined, pooled result of all the studies. Now let's look closer at the box. This square represents the point estimate of a single study. For instance, the specific hazard ratio found in that trial. What's really critical here is that the size of the box is proportional to the study's weight in the meta-analysis. This means larger studies with more precise results get a larger box, and they have more influence on the final pooled result. The horizontal lines that extend from the box are called whiskers. They represent the 95% confidence interval for that study's estimate. This is the range where the true effect is likely to be. The width of these whiskers tells you about precision. A narrow line signals high precision, whereas a wide line signals low precision and more uncertainty. Understanding the horizontal axis is crucial. It changes depending on the outcome type. For ratio outcomes, like an odds ratio or hazard ratio, the plot uses a logarithmic scale, and the null value, meaning no effect, is 1.0. For continuous outcomes that measure a difference, like a mean difference, the plot uses a linear scale, and the null value is 0.0. This brings us to the line of no effect. It's a solid vertical line drawn at that null value we just mentioned, either 1.0 for ratios or 0.0 for differences. The rule for interpretation is very straightforward. If a study's confidence interval whiskers cross this line, the result is not statistically significant.
All right, let's move to Section 3. Here, we'll establish a systematic, 4-step process for interpreting any forest plot you encounter.
This sequence provides a reliable framework. First, you always identify the comparison being made and the outcome being measured. Second, scan the individual studies to visually check for heterogeneity, or how different the results are. Third, analyze the pooled diamond to determine its overall significance. And fourth, you check the I-squared statistic, which formally quantifies that heterogeneity. Section 4 focuses on the main outputs of the meta-analysis. That is, the pooled diamond and the statistics that help us understand heterogeneity. So, we need to answer 2 questions. How is that final diamond result actually calculated, and what do the underlying statistics tell us about how reliable it is? The diamond at the bottom of the plot is the main takeaway. It represents the meta-analyzed aggregate result. The center of the diamond gives you the pooled point estimate, while the diamond's total width represents the pooled 95% confidence interval. For HEOR work, this diamond's point estimate is often the primary clinical input used in the base case of a cost-effectiveness model. Now, this pooled result is calculated using one of 2 statistical models. A fixed effect model assumes that all studies are estimating one single true effect. In contrast, a random effects model assumes that the true effect can vary from study to study. In HEOR, the random effects model is the standard, largely because HTA bodies prefer it. It better accounts for the real-world diversity we see across different clinical trials.
The I-squared statistic is a critical measure you must check. It quantifies the amount of heterogeneity, or inconsistency, among the studies. A value below 25% suggests low heterogeneity, meaning you can use the pooled result with confidence. But a value between 50 and 75% is a red flag, signaling high heterogeneity that needs to be explored. If I-squared is above 75%, it suggests pooling the data is likely inappropriate because the studies are just too different.
And that brings us to our final section, where we'll connect this theory to how forest plots are actually used in day-to-day HEOR workflows.
The most direct application is in economic modeling. The diamond's point estimate, that hazard ratio, for example, often becomes the base case input for a cost-effectiveness model. Then, the width of the diamond's confidence interval is used to define the probability distribution for that parameter in a probabilistic sensitivity analysis, or PSA.
Forest plots also serve as a prerequisite for a network meta-analysis. Before performing an NMA, analysts must review the forest plots for all the direct, pairwise comparisons in the network. If any of those plots show extreme heterogeneity, it suggests that a key assumption for NMA, known as transitivity, might be violated. This could potentially invalidate the NMA results.
A solid understanding of forest plots is also vital for handling objections from payers during HTA reviews. For example, a payer might critique your analysis by claiming the pooled result is only positive because of one single large study. In response, an analyst can perform a leave one out sensitivity analysis, creating a new forest plot for each study that is removed. This can visually demonstrate that the diamond remains statistically significant even without that one influential study.
So, to summarize our session, there are 4 key takeaways. First, the diamond is the most important output. It represents the synthesized evidence. Second, the vertical line of no effect is your benchmark for statistical significance. Third, the size of each study's box visually communicates its weight and influence. And finally, the I-squared statistic helps you determine the validity of the entire pooled result. Mastering this visual language allows you to move from passively accepting evidence to actively critiquing it. With this framework, I encourage you to consider how you might challenge the results of the next meta-analysis you encounter in your work.